my distinct pleasure to have David Schaefer here this morning to talk to us about Siena models. Siena models are the most current solution to a practical solution to these problems of selection and influence that we talked about the last couple of days. And they've always been a bit of a bear to fit. In the old days, it was like in the really old days, it was a real pain in the ass. But Tom Snyder sort of kept pushing them forward. The software kept getting better, and now they're only sort of a mild pain in the ass to do. And brave people do these data. You do these models with data of like 16 waves and nice small networks and this sort of thing. And absolutely crazy people do it on 2 waves or 3 waves with add help, which is what David has done, which I thought was truly impossible. And so he's managed to get more out of these models than anybody I've met thus far, and I think we're just really lucky to have him here. So, David, thanks for doing this. I really appreciate it.
All right, thank you. Glad to see everybody here and with such exuberant faces this early in the morning. So I think it's helpful after a week like this to kind of start with where are we? You've been through been through the ringer to some extent, talking about different kinds of methods, and so I think it helps to kind of break it down and talk about where Siena really fits into this. So here we can, with Siena, we're talking about attributes, behaviors, as well as the network itself. And so what we're doing is putting this together. Some of the methods that you've talked about previously, like yesterday, was the ergoms, which is, we're just looking at the network and we're modeling the dyadic independencies, dyadic, triadic, larger interdependencies between them. We talked, I guess Jim talked about diffusion models the other day. You can think about that as a model where you're modeling an attribute, but not the network, keeping the network stable. So it's more here this network autoregressive, or the network autocorrelation model of Friedkin's. Well, with the Siena model, we're putting both of those together. Okay, we're going to model the network, and we're going to model change in individual attributes. And so the kinds of questions that we're focused on, and I think probably the question of biggest interest, usually among health scholars, is how do networks affect individual behaviors? And I put behaviors in quotes here because it could be any kind of individual attribute that's changing. Maybe it's a behavior, maybe it's an outcome such as obesity. But we're looking at how those behaviors are influenced by the people that we're surrounded by. And with Siena, we can do that quite easily. We can even look at multiple behaviors. I'll talk a little bit about that. How, for instance, your network might affect your eating behavior, which has effects on your obesity. The network might also have effects through other kinds of pathways. We can look at multiple kinds of changing behaviors. But there are other kinds of questions that I don't want people to forget about. And so questions about changing in the network structure over time. And this is, in fact, where Siena models originated, was let's have a dynamic model of how networks are changing. So Tom's original work on this, his 2001 paper in sociological methodology, was just the network and a new model for how we can look at it over time. Okay, and that can be very interesting. For me, it's interesting because, again, if you think peer influence is happening, then kind of the causally prior question is, well, where do we get those peers from? Why do we have the networks who are influencing us? Why do we select people who are good influences versus people who are bad influences? And so modeling this selection process can be very informative and can answer part of, tell an important part of the story as well. Again, we can model one network by multiple networks. What I mean here is we can model changes in something like friendship, but also changes in who you spend time with, changes in advice, these different kinds of relations. We can model all of those within one network and look at effects. Model is all within one model and look at effects between them. We can also look at things like two-mode networks. So think of individuals selecting into contexts or settings. So individuals, I look a lot at high schools, at health data, and you've got individuals joining teams or joining extracurricular activities. You can model those kinds of two-mode networks over time. And then you can put this all together and look at how networks affect behavior, behavior affects networks, kind of look at how these processes play out over time. Okay. So it's a stochastic actor-oriented model. That's the terminology now. A lot of people call it a Siena model. That's actually, I always forget this, simulation investigation for empirical network analysis. It's a mouthful. I think it was a way to get Siena, to call this thing Siena, which is where Tom Snyder's first presented this work, was actually in Siena, the town in Italy. So there you go. So I'll probably call it Siena, but technically it's a Zaum. Some people say I like that, so I might switch to that at some point. But and the big thing here is that we're recognizing that behaviors and networks, they're interdependent. Okay, and there's this reciprocal association between them, and so they're both outcomes. Okay, we can think of we're thinking of kind of the corollary might be something like a structural equation model, where we can have multiple kinds of outcomes, and we're estimating those over time. And the reason we do that is because questions, especially questions about peer influence, have this kind of reciprocal feedback effect that makes it difficult. All right, so here's an example. Let's just look over here at time t for right now, okay? And let's say we have a question about peer influence. We think that this is smoking behavior, and we think that kids influence one another on smoking. And we gather a sample of kids, their smoking behavior, their friends, and we look at dyads, and we see that, okay, people who are connected, here we see two smokers connected, and we see two non-smokers connected. So we see some network autocorrelation on smoking. Is this peer influence? Okay, well, it could be. For peer influence, we would expect something like this to happen, or to be the case at a preceding time point, where A's friends with B, A's not smoking, but A's friend B is smoking, so over time, B is going to influence A to start smoking. And the opposite case, smoking D is shamed by his friend and stops smoking, such that over time we see that, okay, there's this homophily or similarity emerging. Okay, but this could also be happening, right? So it could be that, preceding time point, nobody's friends, and maybe kids coming to a new school, no one knows anybody, but the smokers start hanging out together, the non-smokers start hanging out together, and so that's why we see this homophily emerging over time. Okay, so we really need to be able to parse this out. We need to have data that's over time on both the behavior and the network to be able to really figure out what's happening here. Okay. Now, this isn't just a question about homophily or similarity. This can be, this kind of logic applies to any kind of association between a behavior and an outcome, or a behavior in the network. Okay, so here we have, in this case, smokers being more popular. Okay, smoker has higher N degree, smokers are more popular. What's the source of this? Okay, well, it could be that the network, again, is affecting behavior, that B is more popular, and so that gives B, a little bit more freedom to kind of, engage in any kind of behavior, kind of lead, kind of set the norms for the crowd, and so that might lead to smoking. Okay, or it could be that the behavior affects the network. And here, B is already a smoker. Smoking is kind of among adolescents, that's a sign of kind of maturity. And so that might attract more friends over time, in which case we see that that smoking popularity association emerges because the network changes in response to the smoking. And so what we want to do is be able to kind of parcel out these different competing explanations for why we see, again, we see a pattern between behavior and the network at one point in time. We're trying to get at what's the process that led to that pattern. And there can be multiple kinds of processes at work. All right, so for the questions about, in particular, how the network affects behavior, so peer influence, we really want to control for network selection. Okay, so we want to get at pre-existing similarities in behavior. That's homophily. That's smokers becoming friends with one another. Okay, that's important to control for. We also want to look at similarity on anything correlated with the behavior. Okay, so this is Blau's idea of consolidation, okay, that something correlated with smoking. Let's say at a certain school, the boys are smokers, the girls aren't, okay? The boys start hanging out together, the girls are hanging out together. You're going to see smokers hanging out together because it's really, it's that association with gender. But it's not smoking driving the association, okay? It's gender driving the association. Smoker is just a spurious outcome, okay? So you want to control for those other kinds of attributes that might lead to, the network. And then we also want to get at the network processes, reciprocity, transitivity, popularity. These things can amplify small amounts of homophily or other kinds of, network and behavior patterns. So here, A really has a strong preference for people like himself, picks a couple of friends. All right, reciprocity can take over, right? D chooses A through reciprocity. That's a homophilous friendship, okay? Here, D chooses B through transitivity. Okay? The process here is transitivity driving the friendship, but the outcome is still homophily. So here we've got 4 homophilous relations, but it's really only 2 driven by homophily. The rest are driven by these endogenous network processes. And so we want to think about, again, controlling for these kinds of processes to really get a good estimate of how much is the behavior that we're interested in driving selection patterns. Okay, so with that kind of overview, here's what I'm hoping that we can accomplish today. First of all, I'd like to give you just a conceptual overview of what Siena is doing and kind of how the model works. And then we're going to talk a little bit about model estimation. I'm really hoping, again, for a more of an intuitive understanding of how this works. It's too late in the week, too early in the morning to really get into all of the statistics, but we'll go through enough of it that I hope you understand it enough that you can understand kind of, again, how to interpret it and then how to think about diagnosing kind of poor model fit and fitting models like that. And then we'll go through some examples of smoking, and there is a lot more that we can do with Siena. I'm not going to be able to touch on, but I'll present some ideas, and again, if people have questions about certain things, we can talk about that. Okay, so the Siena model is it's a continuous time model, but it takes these discrete observations. So imagine a network observed at 2 points in time. We have these two matrices, really, two time points. And what we're going to do is model the process that led from one to the other. Okay? And this is actually, it's an agent-based model. And what we're going to assume is that the individuals, the actors in the network, are changing their behavior, changing their networks one step at a time. Okay? And so we're going to specify this. We're going to specify the rules that agents use or actors use to change their behavior, to change their network. And the model in its one of its simplest forms really breaks down into these 4 functions. Okay? So beginning with the network, we've got a rate function that determines how often do actors have the chance to change their ties. How often are they given an opportunity to kind of look around the network and think of drop this tie, add this tie, stay the same, make that kind of decision. The network objective function determines which changes actors make. Okay, so we've got a timing step and then an actual decision about which ties to change. And the same thing for behavior. We've got a rate function that determines how often actors change their behavior and then which behaviors they actually adopt. Okay. These are tied to the observed levels of change in the network. Not directly, they're estimated, but if you think of a network observed at one point in time and then later, there's some amount of change. This rate function gets at kind of the total amount of change. Okay. All right, so here's what the network objective function looks like. Okay. And what we're saying here is that the individual behavior is based upon a set of parameters and the current state of the network X. And we're going to estimate that across a set of effects, okay? And so these effects, SKI, represent all of the different selection processes that we could put into the model. Okay, we've got a set of effects, and then each one is given some kind of weight. Okay, now these effects could be based upon the network, something like reciprocity. It could be based upon attributes like smoking. We're going to put a set of those in, and then the goal of the model then is to estimate the values of these betas here. Okay. Now, how does this actually work in practice? Okay, so it's actually, again, it's an agent-based model, and so we're going to simulate over time from one wave to the next. Every actor's, we're going to give every actor opportunities to change their networks. Okay, so we call these microsteps. Okay, so we've got a series of perhaps 1,000 microsteps from one observation to the other, and we're going to give every actor a chance during a microstep to evaluate their current network, evaluate each dyad, whether there's a tie there, whether there's a knot, and give them the chance to change, make one change. Okay, and the goal of the actor is to maximize this objective function. Okay, so make the change that produces the greatest kind of, you can think of it as a utility function, produces the greatest utility. All right, so here's a very, very simple model. It's got only out degree and reciprocity. Okay, so out degree and just a couple of parameters just thrown in there for now. So out degree is really, again, for actor I, the sum across xij. So for ego here, right, out degree is the sum across all of the j's there, out degree of 2. Okay, and then reciprocity for actor I, across all of our j's, we're going to look at whether or not ij and ji match. So for ego, looking at j1, we're going to compare ego j1 to j1 ego. It's reciprocated. We're simply going to count up those for each actor I. We're going to count up those across all of the alters j. Okay. So again, we've got this simulation running, and it's ego's turn to make a decision. And ego has 4 other actors in the network. Which choice does ego make? Okay. Ego turns to the current state of the objective function and evaluates each dyad using these parameter values. Okay, so let's start with ego decides I'm to not make any changes. Okay, that's what I just walked through. Okay, where ego has an out degree of 2 and 1 reciprocated tie. Okay, we simply plug those in, sum it all up, and those effects contribute to a negative 2.2 to the objective function. Okay, that's not a very pleasant state of affairs, mainly because there's not a whole lot of reciprocity. Well, I'll get to that in a minute. Okay, so ego makes no change. The value of this utility function is going to be negative 2.2. Let's say ego drops the tie to J1. Okay, tie's already there. If we drop it, that's going to reduce the out degree. Okay, only 1 outgoing tie drops that count. That's the only reciprocated tie, so it drops that count. We do the math. The utility of that decision, negative 2. Okay, a little bit better than making no change. Okay, so that's already a little bit more attractive network from ego's perspective. All right, dropping J2. J2 is a tie that, again, dropping it would drop the out degree by 1. It would keep reciprocity the same, right? Because it's dropping a tie that's not reciprocated. Okay, and reciprocated ties are valued here. Okay, so there's actually a penalty for sending a tie that's not reciprocated. Okay, and that's reflected here in the higher value of the network function for that decision. Okay, and then we got a couple other decisions, neither of which is very attractive. Adding a reciprocated tie to J3 is attractive because it's a reciprocated tie, but it's adding another tie. Okay, and the negative value of that degree says adding ties is kind of, we're not going to add ties unless there's a really, really good reason. Reciprocity is a good reason, but it's not good enough that we're going to add it. You look at adding a tie to J4 here. It increases the out degree statistic, has no effect on reciprocity, so its utility is way low. That's probably the worst decision that ego could make here. Okay, so what ego's going to do again is calculate all of these functions, add a little bit of error to that calculation so that it's stochastic, and then adopt the change that produces the highest utility or the highest value of this behavior function. So in this case, that's going to be dropping the tie to J2. Yeah?
I might have missed the sort of overall. So what is the utility function is, I get the sort of the notion of a utility function. I want higher utility, but what is higher utility sort of defined as in this context? If I was in balance theory, I'd go, oh, I want balanced triads, and the more of those I had, I'd have a higher utility. In this context, what are the agents sort of striving for?
Right. It's based on your model specification.
I see.
So in this case, it's really reciprocity is the only thing. They're striving for reciprocated ties and not too many ties. So that's the negative out degree is.
I see.
You're not just going to add ties. You'll add some that are reciprocated, but there's some kind of equilibrium. Yeah.
If you had undirected, then you would just take that term out?
Correct.
Okay.
Right. Yeah.
I might have missed this. What's the -2 and the 1.8? Where are those values coming from?
Good question. Those are, I made those up. Those are what you're actually estimating. So they are, I'll talk a little bit more about this in a minute, but the goal is to find good values of those. And so you're going to estimate them kind of provisionally, early in the model fitting, and then iteratively let actors do this and kind of see how it ends up.
So those are the betas?
Those are the betas, yes. Yeah. Yes.
What's the implication if you have a subset of all possible network types?
So,
Let's put something with make sense, I guess, if you do every possible choice.
right.
But if you don't do every possible choice.
So that is an assumption of the model, is that you've got some bounded setting where all ties actors can evaluate all possible ties. So it may not, if you don't have that kind of data, it may not be suitable. Yeah, we can talk about that. So yeah, that's ego network data. Isn't really suitable for a Siena model. Yeah.
This may be a dumb question. Do you think that this is how people decide their networks in real life? Or like, I'm sorry if it's dumb. I don't want to be like.
Right.
It's like a very rational actor kind of.
It assumes a rational actor. It acts as if an actor is rational. You don't have to necessarily make that assumption, because again, you're just looking at these tendencies over time. It's a way to kind of achieve this MC. It's really a Markov chain that you're generating. It's just another way to do it, different from what you talked about yesterday with the ergons. Yeah.
So in this case, ego, it makes sense for ego to drop J2, but from J2's perspective, what if it's an outgoing tie? So it's an incoming tie. So what if he wants to keep that? What if he's maximizing functions to keep it? Does it depend on like the bargaining power or?
Right. So the Siena model, it assumes with the directed network, it's assuming that each individual only controls their outgoing ties. Okay, so J2 could add a tie to ego, and that might be enough, for the model for ego to keep that tie. With the actually undirected networks, you can make different kind of assumptions about whether or not you impose a tie or you kind of propose a tie and someone agrees to your tie. We're not going to get into that. But
Sorry, maybe I missed this. Does this also assume that people's preferences for the kinds of networks they want are uniform throughout the study population? Like that everyone wants this, or maybe there's some people more introverted, extroverted, want reciprocated, want more dense level networks, want sparse ones, that sort of thing.
right, we'll get into that, I think, a little bit. But right now, the assumption is yes, homogeneity. Every actor has the same utility function. You can very easily start to kind of, you can estimate if you have kind of a priori ideas of where that heterogeneity is coming from. You can include that. Letting it emerge, we're not there in terms of estimating.
Just letting it let those coefficients vary by person.
Right. Right. Yeah. All right. All right. Good questions. All right. So some of the effects, I guess this will start to answer your question. Out degree, we're always going to have out degree. This is basically controlling for the density of the network. Okay, and we're going to keep it usually, density is quite low in at least kinds of social friendship networks that these models are used for. So you're going to see out degree, and it's usually going to be negative. Network processes, reciprocity, transitivity, popularity, in terms of some individuals have more ties, they also tend to receive more ties over time, kind of the Matthew effect. We're going to control for that oftentimes. Sociality. So this is how I interpret your question. Some kinds of individuals tend to send more ties. And if we have information on what that might be, whether it's personality, we can include that. Oftentimes, if we're even just looking at something like smoking, and we're interested in smoking behavior, we'll include a smoking out-degree effect or a smoking ego effect to control for the fact that smokers might be sending more ties than non-smokers. Some kinds of individuals might receive more incoming ties, and so we can have popularity or in-degree based upon an attribute. Homophily, and all of these things, again, they can be stable, time-changing. We'll get to that in a little bit. We also want to include oftentimes dyadic kinds of attributes. Okay, so network processes, individual attributes, and then dyadic things such as co-presence, or other kinds of kind of relational things that, again, you have measured at for the whole network. So not necessarily relationship strength, but maybe kind of, again, co-presence or co-membership or any other kinds of similarities. Okay, so we're going to, again, the behavior function predict change in behavior over time. And again, this is optional. So you can estimate a Siena model without any kind of behavior change. Okay, a lot of those, I've done that. Sometimes it's sometimes a lot better because it's a lot faster if you're not looking at behavior change. Just looking at network change, you get a model in much more reasonable amount of time. But one of the things that is important to remember is that as of right now, the behavior measures need to be ordinal, okay, with just a small range of values. And this gets at kind of the model, how the model works, this actor-based nature of the model. Actors make kind of these changes in levels of the behavior. Okay. I'll show you that here right now. All right, so this is the form of the behavior function. It's actually quite similar to before. We've got some parameter estimates, the network, and then also a behavior here that is informing our decision. Okay, and the behavior function determines for an individual actor, kind of given the level of the behavior that they're at, where do they go next? Okay, so let's say we've got some behavior, individual is here, do they stay the same? Do they decrease by a step, or do they increase by a step? Okay, so again, this is kind of analogous to the network function, where an actor is allowed to make just one change at a time. Okay, one actor is allowed to make one change. In this case, they're moving one step on this behavior. And we're going to do the same thing as in the network function. We're going to allow the actors to evaluate every option and then make the change that creates the highest value of this behavior function. Okay. So the function itself is going to have, first of all, a linear term. This is kind of like an intercept, okay, to control for the overall distribution of the network. It'll have what's called a linear term, which really just gets at, again, the distribution. That's not going to make a whole lot of sense yet, but I just want to mention it because it's there. Of interest, usually, for most people, is the predictors of peer influence. So we want to know, how does alters level of a behavior or other alter attributes affect individuals' behavior? Okay, so we're going to include that in the model, and then we might include some individual level controls. So for smoking, we might include gender, age, network position, interactions with the network, things like that. Okay, so here's an example of what a behavior function looks like. And again, those are betas up there. The numbers are betas that are just thrown in there for now. But we've got a linear effect, which is really as an ego is evaluating kind of different options. We're going to evaluate where ego currently is on the behavior. Okay, so the behavior actually is endogenous to here. We're going to include a squared term of the behavior, which allows for nonlinear kind of feedback effects of current level of the behavior on itself. Okay, so some behaviors are self-reinforcing. Some smoking is addictive. Okay, so people who smoke a lot tend to keep smoking. People who don't smoke tend to keep not smoking. And so this allows for a curvilinear kind of feedback effect of the network or of the behavior on itself. We can also include attributes. Okay, so we can include, again, the interaction between the behavior and ego's attribute V here, and some kind of mysterious similarity effect here, and we'll unpack that shortly. Okay, but that's what a very simple behavior function is going to look like, and what we're going to do is ego's going to ask, based upon all of these things, what's going to maximize, what level of behavior is going to maximize my utility. Okay, so I promise this is the most math of any slide here. This is simply unpacking what similarity is. Okay, this is, if we want to get a peer influence, the similarity, this kind of similarity effect is important to understand. All right, so when ego's deciding which level of behavior, ego's considering alters through this effect. And what it really is the similarity. If ego adopts a certain behavior, how similar will ego be to all of the alters? And then we're centering that based upon just the average level of similarity in the network. Okay, so is this behavior going to make me more similar or less similar relative to the average of the network? Similarity itself is simply the difference between ego and alter's behavior. We take the absolute value so that we're just looking at difference. Subtract it by 1 divided by the range. Let's see. Divide by the range, then subtract by 1. What that does is first of all, it turns similarity into something that ranges from 0 to 1. Okay? 0 completely dissimilar, 1 completely similar. And the 1 makes it so that you're talking about similarity versus dissimilarity. So I don't know if you talked about, with ergoms yesterday, if you talked about the absdiff effect and how you're taking the absolute difference to measure homophily, so you get negative, an absdiff coefficient that's negative, which means there's more homophily, which is very confusing to some people. So this just makes it scaled in the right direction. Okay. So when we're calculating total similarity, what we're doing is, what's the difference between ego an alter, summing across all of the alters, and putting it on this, for each dyad ij, we're putting it on this 0 to 1 scale, and then we're summing across all dyads. Okay. All right, so let's walk through what that might actually look like in practice here. Okay. So currently, this is the same network as before. We've added some behaviors here. He goes at level 1 as our J1 and J2, and then J3 and 4 are one level below and one level above. And ego is trying to decide what level of behavior am I going to adopt based upon this pattern, these ties, and the behavior of alters. Okay, so let's first consider just maintaining the same level of behavior. Okay, ego is going to stay at level 1. What does that mean for the total similarity in each dyad? Okay, so in J1, ego's got a tie here to J1. The similarity here, work out the math here. Similarity is 0.5. Compare it to the centered value of similarity, which is something that we just calculate based upon the whole network once. And that similarity winds up being 0.45. Okay. Same thing for J2. J3 and 4 add just a tiny bit of similarity here because of, again, the difference here in their behaviors. Okay. I just realized this should be 0. All right, ego does not have a tie to J3. Okay, so this should be a fat 0 right here. Okay, because we can calculate the similarity, but because there's no tie, doesn't matter. Right, so that should be 0. Drops that down a little bit. My apologies there. Okay, so, all right, so ego's calculated. If I maintain the same behavior, this is going to contribute 0.95 to that behavior function up there. All right, what if I changed? What if I dropped down to 0? What would the value of that be? Okay, we go through all the same steps here. Right, dropping to 0 makes ego different from J1 and J2. Okay, so those similarity scores are going to drop down. Becoming 0 makes ego more similar to J3, and if there were a tie here, it would be 0.45. So that would be kind of a draw. Dropping to 0 produces even greater difference here between ego and J4. So very unattractive, plus there's no tie. So there's very little kind of incentive for ego to drop to 0 via this tie down here. Yeah.
So when you're talking about summing over all of ego's alters, you're counting J4 even though ego doesn't have a tie to him, and that equals out at 0. So if we're dealing with sociocentric data, are all of ego's alters everyone else within that space, like everyone else in the sociocentric network, or are we like asking about the boundary, I guess?
We're if this were a network of 100 people, we would be calculating this for all 100, but most would be zeros.
Okay.
There might be a shortcut in the algorithm, so you don't have to do all those calculations. But in theory, that's what's.
So it's out of the range of possible alters with whom you could have a tie.
Right.
Yeah.
Right. With the behavior or the network function, you are considering every alter in particular. Here, we're considering every behavior within a step of 1 and how. Really, and the ones that matter are who you have an outgoing tie to. Okay. All right. So we could do this one more time if Z is going to increase behavior up to 2. That would also make make ego different from alter 1 and alter 2. Would make ego more similar here to alter 4, which would be a good thing, but there's no tie, so again, not very appealing. And so ultimately, okay, so that gives us all of that just to calculate the contribution of this total similarity statistic to each of these possible behavior choices. Ego is also going to consider these other effects in the function. Okay, so that's what we get here. These are the three choices. Okay, drop to 0, stay at 1, jump up to 2. Here's the contributions of similarity that we just calculated. The linear, quadratic, and age terms also come into play. So the linear term is negative. So higher levels of the behavior are actually less attractive. Okay, so you see here, you weight the current level of the behavior or the current level of the proposed behavior by a negative 0.5. So dropping to 0 is attractive. Staying at 1, not really attractive. Going up to 2 is even less attractive. Okay. But the quadratic term, we need to consider that as well. So we're actually going to, in summing those up, you can see that there's actually a U-shaped distribution there. I'll show you that in a minute. Age is simply take the current age and then multiply it by the parameter and multiply by the prospective level of the behavior, and that's what's going to give us the contribution of age. Okay, so we're going to sum across all of these to get at the value of the behavior function itself for one actor. Okay, and so this kind of summarizes what the model is, kind of how the different parts of the model are pulling the actor in different directions. The linear and quadratic terms in combination pull ego in one direction or the other, okay, either towards smoking or away from smoking. The positive coefficient for age pushes towards higher levels of smoking, so older kids more likely to adopt higher levels of smoking behavior. And then the similarity function has this weird slope here. Okay, we have an inverse U shape, but in this case it's pushing ego to stay the same, and that's because the two outgoing ties are at this level of 1. Okay, so ego is likely to adopt or to stay at this level of 1. You know, even though it's even though smoking overall has this weird distribution, the fact that ego has two alters who are at this level of 1 is going to keep ego at level 1. All right. Yes.
So for this, you have to choose kinds of behaviors where you can undo, like you can change things. So I'm thinking like something like sexual debut, right? So you could have a 0 and then you can go to 1, but then once you're at 1, you can go back to the 0.
Great question. Right. So there's a couple of answers to that. You could estimate that with the behavior function just like this, and the model actually respects the fact that behaviors only increase. Okay, so you could do it that way. You could also, if there are behaviors that only decrease, the model also respects that. The same thing for networks. If there are, if it's a network that's only growing or only shrinking, then that constraint is kind of it's built into the model. Another way to do this is to, I'm going to talk about the rate function, but you can actually model let me talk about the rate function, and I'll try to remember to say it there, because I think it'll make, right. Okay, so the rate function, it's included in both the network and behavior. I say that, but there's an option to do to estimate the network conditional on the observed number of changes, in which case you don't need a rate function. You just allow actors to change a certain number of times. But for unconditional estimation, you are also estimating a rate function that kind of dictates how often actors are given the chance to change their network, how often they're given the chance to change their behavior. The rate function is really, it's again based on the observed number of changes between the waves. Okay, so you might see 100 ties change between two waves. Okay, so every actor has some number of changes kind of based upon that. It's not exactly whatever 100 divided by the number of actors is, but it's a function of that. The function is really, again, in this, it's the waiting time for each actor until they get the chance to make a change. Okay, so if we've got a network of 100 actors, basically it's a way to pick one actor, give them a chance to change, pick another actor, give them a chance to change, pick another actor, give them a chance to change. And the function is uniform across all actors, meaning that kind of anybody has the chance to make the next change. Okay, so on average, everyone gets, say, 10 chances to make a change, but there'll be some distribution there. And we could actually model whether some actors get more chances than others, and we can also model, which is another way of saying some actors have an earlier chance to make a change than others. Okay, so this starts to get at kind of your question. And so for something like sexual debut, what you're wondering is, do some actors have the chance to debut earlier? Or do some actors actually debut earlier? And so you can actually model, estimate a model that puts alter attributes into the rate function for the behavior. And so you can estimate the time, essentially the time to a behavior based upon alter attributes. And so what you would expect is that egos who have more friends who've debuted, you can include a peer influence kind of effect. If you have more friends how does friends' level of debut affect one's own kind of likelihood, and test whether, again, those individuals have an earlier chance of debuting than others. And it works out to be just a Cox proportional hazard model. It's almost exactly the same. The difference is you also have a changing network. So that set of alters is changing continuously. Okay, but we've done a little bit of playing around with this, and you get very similar answers, especially if you estimate a Cox model with kind of more frequent updating of the network. It starts to look a lot like this. So you can think of it as a Cox model. Okay, yeah.
So when you do a rate function, you're making the assumption that there is a succession of change, but that they're not necessarily debuting together, or
not at the exact same time, but you could estimate, yes, that if an alter debuts, that you're very much likely to debut the next chance you get and have a sooner chance. Yes.
but they're not necessarily debuting together.
So right. So
Sorry, I'm just trying to figure out what would be.
right. So one of the assumptions of the model is that there's no coordinated action. Okay, so you can't have two changes at the exact same time point. Okay, so if we're looking at, yes, a dating or romantic network, you're not going to get two people linking and debuting at that moment, at least not through a behavior function. If you think about it as a sexual network, though, and actually, coupling as a tie, you could get that. You could think of that as a simultaneous debut. Yeah, good question. Yeah.
I'm just trying to wrap my head around the temporality of it, because we were talking about maximizing the network objective versus the behavioral objective, and that similarity. For that one example, it was in the maximized utility to drop the tie to J2.
Right.
But then we still use that time to look at the similarity
Oh.
of changing your behavior. So is the maximizing the behavior objective based on your previous ties, or does it kind of simultaneously?
No, great question. Am I gonna get to that? It's too technical later. I'm probably gonna skip it actually. But so what the model does is there's a rate function for the network change and for the behavior change. And well, actually, I'm gonna skip up to it. This might make more sense. So what is happening during the algorithm is you take the network and behavior at the first observation, so that first wave of network of behavior. Every individual with the rate function has a chance to be the next change in the network or the next change in the behavior. And so every actor kind of basically gets a random value from the rate function. Okay, and so the model determines what's the shortest waiting time, which at the actor level, either my behavior time is my behavior waiting time is shorter, or my network waiting time is shorter. So for every individual, it's one or the other. And for all of these decisions, if it's me and it's my time to change my behavior, I look at the network as it is right now. Okay, and if I drop J2 before, it's gone. And so it's continuously the network. Every time an actor has a chance to change their behavior, the network probably looks a little bit different. And every time you're changing the network, the set of behaviors probably looks a little bit different. Okay, so yeah, this is just a little bit what's happening when the model is actually estimating this process here on this side is just how each individual actor decides whether or not to change their network or to change their behavior. And what we're going to do is just go through this loop a bunch of times, determined by the values of the rate functions. Okay, we're going to go through this basically until we get the amount of change observed in the network and the amount of change observed in the behavior. Okay, we're just going to do this a bunch of times, and what the model itself is trying to do is, again, we're trying to identify betas, trying to identify some parameter values. And we know we have good parameter values when we're able to, the model is able to create some networks that look like the network we observe at time 2. Okay, so we have these target statistics, okay, that are basically the effects in your model: reciprocity, out degree, similarity. We calculate, we use those target statistics, or we use those statistics to calculate the observed levels of those at time 2, and then we're trying to recreate those with, find a set of parameter values that are able to recreate those. Okay, and we're going to do that in 3 steps. We're going to initially estimate some parameter values, some betas. So the question earlier, where do those betas come from? We're just going to get a rough estimate to start. And then we're going to go through a bunch of simulations to kind of narrow in on better and better and better and better estimates that get us closer to these target statistics. Okay, and once we think we're pretty close, then we're going to do some more simulations, take the network that's estimated, the set of parameters that's estimated, generate a couple thousand networks based upon that model, and see if those generated networks, well, we're going to use those to calculate some standard errors, but also we can use those to see how well our model fits the data. So did you get to goodness of fit yesterday? Yeah, okay, so we can use those for that kind of process as well. Okay, so we're actually, if you see, we have simulations here to get good parameter estimates, and then we have simulations here, down here, to get some standard errors. It's the same simulation. Okay, we're doing the same simulation in both steps. The difference is, in this first step, we are calculating, we're updating the betas each time we go through. Okay, so we simulate the network, we go through, give each actor a chance to change their ties, change their network, and then we take that final network behavior set that's created, and we compare that to our target statistics. And are we close? Are we off? Update. We'll update the parameter values in a way that we think is going to get closer. Okay, so if we run a model and there's not enough reciprocity, well, maybe that reciprocity parameter needs to be stronger. Okay, so up that a little bit. Okay, and then run the simulation again, see if we get closer. Okay, and that's what we're doing here. Okay, so we run the simulation, okay, until time's up. Okay, this is one simulation run. Okay, all actors change their network and behavior. One simulation run, though. And then we store that. Have we reached the maximum amount of simulations we're going to run? No, we haven't. We're going to update our parameters to try to get closer. And then do the whole thing again. Okay. Do this again. Store the ending network. Again. If we're still in this phase 2 or updating the parameters, we'll do that. Yeah.
For the rate function, is it always, so you said you can either change the network or the behavior first. So if you change the behavior first at iteration 1, are you always changing the behavior first for every subsequent iteration, or is it evaluated each time in terms of which is the shorter period?
Right. These waiting times are drawn kind of each step.
Okay.
Each micro step, every actor draws a new waiting time.
Okay.
So you're starting to, I think, see why this takes so long to estimate. You're drawing those new ones each time. Okay. So that's what's happening under the hood. So by the end of all of this, we will have a set of parameter estimates. Okay, some standard errors. We want to know how well this worked. So first thing we're going to do is check for convergence. And here, convergence occurs when the network is able to create a distribution of these target statistics that's centered on the observed target statistics. Okay, so what does that mean? That the model is able to generate a distribution of networks with the same level of reciprocity as the observed network, the same level of homophily as the observed network. Whatever effects are in our model, the same level of correlation between age and smoking that's observed. Okay, and we actually can evaluate convergence. There's a T ratio that's really how much does the observed differ from this distribution. Okay, so we've got a T value here that we want to be quite small. We've got a maximum convergence ratio that we also want to be small. And the idea is if convergence isn't reached, then first thing is there's a few steps involved, but basically we're going to rerun the model, give it some better starting values, and see if we can get closer. Usually that will work.
Question. So the convergence, these are the parameters that we put into the model. These aren't like the other, we're testing specifically what we put into the model. We're not like let's say gender was something that else that we were interested in.
Yeah.
Or like that, but we didn't put in the model. We're not checking to make sure that like the gender, is that in the model, right?
If gender were in the model,
Then we'd
let's say
model.
gender homophily.
Yeah.
That would be there would be a target statistic. There is this level of similarity in friendships based upon gender. This level of gender homophily. Does the model estimated parameters produce networks that have that same level of gender homophily? If gender homophily were not in the model, who knows where we would be? But that gets to the next point, which is if convergence is good, we want to estimate fit. And so fit is the best way we have right now to characterize fit is, does the model produce things that aren't in the model as well? Does it? So I think you probably talked about this yesterday with ergoms. It's the exact same idea that you want the network to produce other features, the model to produce other features of the network that weren't explicitly modeled. You also want that with behaviors. You want to predict behaviors and distributions, perhaps distributions of the network and behavior that aren't necessarily in the model. Okay, so we might want to, if we're looking at smoking, we've got a smoking similarity effect, but we might also want to look at how much there's not just autocorrelation on smoking, but autocorrelation within certain distances. So are people at distance 2? Is there? It really gets at clustering. Are people in clusters where there's a lot of smoking, and you can get at whether people near the network but not directly connected have similar levels? That's not something we're modeling, but we could. Hopefully, we're getting close for that as well. Okay. All right, now I think might be useful to walk through an example of kind of fitting a model and how we interpret the model. And so this is some work that I've done on ad health data. And this is looking at just the 2 in-home surveys, which they're nice in a way in that you've got networks observed at 2 points in time, and then a wealth of kind of behavioral and attribute data. There's an earlier wave that's got network data, but more limited behavioral data. If you're interested in questions about network change, it's good to enclose those 3, but you can't get a lot of behaviors that you want to get at with that. Okay. All right. So here is probably after yesterday a horrible visualization of smoking in the network, and you can't really tell, but there are a few more smokers. I think it's this region that's got a few more smokers. There is some homophily on smoking in the network. All right. So I want to. We estimated a model. We estimated a model to try to get at peer influence on smoking, but also controlling for selection into relationships based on similarity on smoking. And then we also had a question about smoking and popularity. And is it popularity leads to smoking, or is it that smokers become popular? And so we want to parse out these 2 kinds of associations using this. And so I'm going to present some results, and just in terms of thinking about interpreting the model, if you can understand kind of the estimation, everything, that's great. Sometimes it's challenging, especially when you're first getting started. So you can really think of this a lot like a logistic regression, okay? So, and really a lot like like an ergo. The difference is you're not modeling ties at time 2. You're modeling change over time, which is it's a subtle difference, but it's important. So what the model is doing is modeling which ties are likely to be either added or maintained over time versus not added or dissolved over time. Okay. So you are modeling that change, but you can think of it like logistic regression. So with that, you can even think about modeling or interpreting some of these effects. You are modeling the log odds of a tie, okay, just like logistic regression. You can think of using an odds ratio to interpret some of these effects. But the caveat is, it would be, what is a 1-unit change in your independent variable? How does that affect the odds of a tie? Okay, that would be the interpretation. All else being equal, right? So how much does adding a reciprocated tie, going from 0, a tie that's not reciprocated being 0, to a tie that's reciprocated being 1, how much does that 1-unit change affect the odds of a tie? Okay, so again, you can think of it that way, but you have to keep in mind that adding a tie is also changing the out degree. Okay, so you're not keeping everything else equal. You're never keeping everything else equal. Okay, but if you were, you can think of it that way. All right, and then the behavior function also gets at the same idea. How does a 1-unit change in the independent variable change the odds of increasing behavior by 1 unit? Okay, sometimes 1-unit changes mean something like reciprocity, or in the behavior function, a 1-unit change could be an increase in age of 1 year. Okay, that's meaningful. Sometimes it's not meaningful. So when we think about how does average similarity between me and my friends change by 1 unit? Okay, that's a really complicated statistic. It's not really clear what a 1-unit change is. So I say this because if you read the literature, a lot of times you might see people talking about odds ratios. And sometimes it makes sense. A lot of times it doesn't. And kind of this is why. Okay, that 1-unit change is ambivalent at times. Okay. All right, so here's an estimated model. Okay, and this is actually a quite simple model, right? It only has 24 effects or so. But I want to walk through a couple of things. So this is just the network function. We have the behavior function. I'll get to it in a little bit. Okay, so this is just predicting change across those two waves. Okay, the rate function, value of 10. So each actor is given about 10 microsteps. Okay, has about 10 opportunities to change their network. Okay, and they can, again, for each of those, add a tie, drop a tie, make no change. Okay, so because of this, sometimes actors make no change. Sometimes they might add a tie and then drop that tie. So the actual number of changes isn't going to be 10 changes per actor. Okay, that would kind of be ridiculous. But that's the number of opportunities. Okay, and then here we have this is actually what the effect looks like, the rate effect. And really here we just have a parameter. Okay, the rate effect is super simple. Okay, it's just one parameter, no inputs here. And this is the short name for the effect. When it comes to actually estimating or setting up the model within our Siena, this short name is how it's referred to. Okay, that'll make more sense later, but I want to have it here so you can refer to it later. Okay. Here is the density effect, or the out degree effect. Negative sign is typical, kind of like with ergms. Oftentimes you have a negative edges effect. It just means that the odds of a tie is really low unless these other things are occurring. Okay? You're not just going to go out and just add ties. Okay? So the effect is actually called density within our Siena. This is this is how it's calculated, just in the network for individual I, how many ties do they have? Okay. Now, I've been talking about target statistics earlier, and we want to try to have a model that represents these target statistics. Okay. Since density is in the model, okay, it's always in the model. The target statistic is really this function summed across all egos, right? That's so for individual I, right? How many outgoing ties does I have? We sum that across all i's, we get the total number of ties in the network. Okay, that's the target statistic for out degree. Okay, so we're trying to come up with a value, a parameter estimate for out degree that, when combined with all these parameter estimates and run through this simulation, produces an out degree that matches what's observed, and or a distribution that's pretty tightly centered around that out degree. Okay. All right. Reciprocity has a positive effect. Okay, so actors more likely to add these ties that are add or keep ties that are reciprocated. This value of around 2 is pretty standard in friendship networks. Transitive triplets. This gets at our local clustering, and I think it's useful to look at these also as an exercise in some of the statistics aren't this simple. And so understanding kind of what an effect is doing, you really need to work through here. Right? So this is really a tie from I to J times a tie from I to H times a tie from H to J. This transitive triplet that I think you probably talked about the first day. A lot of detail. So again, we're just summing or multiplying those together for each pair of actors J and H. How many transitive triplets does a potential tie create, and then summing that up across the whole network for the target statistics. Now, since I've run this model, when was this? This was 2012 paper. It turns out that oftentimes reciprocity and transitivity don't work together. Transitivity and reciprocity kind of they're both really strong effects, and oftentimes you don't need both of them in operation to get a tie. Okay, if you're in this kind of transitive triplet, you've got a direct tie to someone, also an indirect tie to someone. It's kind of overkill to have both of these effects promoting the tie. So oftentimes there's an interaction between those two that is negative. It's kind of one or the other is sufficient for a tie. You don't need both. So it's a good idea to include an interaction between transitivity and reciprocity. Improves the fit quite a bit. All right. So this popularity statistic is really getting at, are ties more likely to alters who have lots of incoming ties? So that's the in degree of J. Okay, so we're multiplying J's in degree times whether or not I has a tie to J. And the positive coefficient here means that if an alter has more incoming ties, they're even a little bit more attractive to add or keep ties to. Okay. We have a dyadic covariant here. Whether or not for each dyad the two individuals share at least one extracurricular activity. We see here with the statistic, so this W here is actually, it's a matrix, it's the same dimensions as our network, and for each individual I and J, do they have a tie, do they not have a tie? Subtracted by the average level of overlap. Okay, so we're actually centering this covariant, and this is a good time to mention that all covariates are centered by default within a Siena model. We'll see that a little bit on when we start talking about similarity, but that's something to keep in mind when it comes to interpreting effects, is that these things are internally centered, so to get back out estimated or predicted effects, you need to take that into account. Okay. All right, here are the effects for a bunch of different covariates. Okay. We see homophily here on gender, age, alcohol use, and GPA. It's this similarity effect. Here, we're again, for each dyad, we're just looking at how similar they are. This is the same similarity formula that I showed earlier, centered by average similarity within the network. Okay. For gender, we can also code this as just same versus different. Just 0, 1, same versus different. We get actually a very, interpretation-wise, we get the same answer. We also have ego and alter effects here. So this gets at the tendency to, ego effects get at whether or not certain kinds of individuals are more or less likely to send ties. Okay, so you see here again, ego's attribute V multiplied by ego's out degree. Okay, so is out degree higher, basically, or lower for certain kinds of individuals. And then this is just, again, alters attribute multiplied by the network. All right. And then, so the big question for this paper was looking at smoking. And what are the selection effects on smoking? The smoke similarity is our homophily effect. Okay, more similar kids on smoking tend to become friends or stay friends. And then alters who smoke are more attractive than non-smokers. Okay. Now this homophily effect is really, it's an interaction between ego and alter. Okay. In this case, it's it's not just multiplying the two together. We could do that, or we could do this other kinds of similarity function, but it represents the joint values of ego and alter. And so the same idea behind interpreting interactions in linear models apply here, in that we want to take the main effects into account when interpreting. Okay. So the easy way to do that is to calculate basically the predicted probabilities. Here it's predicted contributions to the network function for different values of the attribute. And we're going to look at the dyad level. Okay, so we're going to look at different kinds of dyads, each possible kind of dyad, and how much smoking of ego and smoking of alter contributes to the likelihood of a tie. Okay, so to do that, we actually, like I showed you earlier, look at the behavior function or look at the network function and plug in values for ego, plug in values for alter, plug in their similarity, and calculate the contribution to the network function of those effects. And when we do that, we get these numbers here. All right, so we've got homophily on smoking because if you look at the diagonal, okay, non-smokers, choosing non-smokers, that contributes this 0.25 to the network function. Okay, that's attractive. Smokers selecting smokers contributes a little bit more to the objective function. Okay, so that's attractive. The off-not diagonal here shows us that non-smokers not likely to select smokers. Smokers really unlikely to select non-smokers. Okay, so there's some asymmetry here in these ties where smokers tend to be a little bit more exclusive than non-smokers. Okay. This is, I can't emphasize it enough how important this is because sometimes some effects, when you get similarity effects but also some alter and ego effects, if you want to interpret this as smokers are popular and there's homophily, yes, that's true. You can kind of see that here. Smokers have a smokers are more likely to be selected than non-smokers, but it's not uniform, right? You've got these differences across levels as well, and that's not always apparent just looking at the coefficients themselves. Okay. All right, so now turning to the behavior function itself. Here we're predicting smoking, and students have about 2 chances to change their smoking behavior. Not a whole lot of change. Okay, the linear and quadratic terms here represent the distribution of smoking over time. Okay, we're trying to get just that rough distribution of smoking. Okay, and these are another kind of part of the model that can be difficult to interpret. Yes.
Sorry. Maybe I should have understood this right, but what does the interpretation of the rate coefficient mean and the significance of it?
The interpretation, again, is just the number of microsteps.
That's it.
That's it. And significance is it's not 0. I mean, it's kind of.
So would you ever expect it to be 0?
I would not. No, and you really wouldn't even want to. There would be no point in modeling. Really, if it were 0, you could stop if it were 0 and just okay, it's not really changing.
Nothing's changing in your network.
Yeah. Yeah. I mean, that might occur, especially if you have number of waves, and eventually some things reach equilibrium. Everybody sexually debuts at some point, and there's no change. Okay. All right. So the linear and quadratic terms, I think it's helpful to actually look at what these, how to calculate these. All right. What this is telling us, if we take the actual possible levels of the behavior and plug them into our equation, we're getting predicted the contribution to the behavior function, kind of how likely each of these levels of the behavior is across kind of all actors in the network. Okay, we're centering here. Like I said, all the covariates are centered, so that's taking into account. So I didn't show you the actual distribution, but it looks pretty close to this. We have some kids who smoke at this middle level, but it's a U-shaped distribution, and that's all that the linear and quadratic terms are trying to do. There's a tendency, a horrible tendency, to interpret the linear term or the quadratic or this set of effects as individuals are likely to increase or decrease, right? So if that linear term were positive, and we know that the model is modeling change, there's almost this innate desire to interpret that as, well, that's a change in the positive direction, okay? But that's not what it's doing at all. All it is trying to do is get at just this base distribution, and then these other effects in the model are going to talk about, well, why do some individuals kind of vary around this distribution? Yeah.
Sorry, 0 to 1 is 10 to 1, 0 to 10 is 10 to 1.
No, these are smoking levels here, and these are smoking levels down here as well.
over time, right?
Pardon? No time. No.
So, well,
These are non-smokers, moderate smokers, and heavy smokers, say.
Exactly. Right. So this is right. So this is how much. Again, when actors are choosing a level of behavior, this is not smoking has a certain level of attractiveness. Smoking at a moderate level has this level. Smoking at a lot has this level of attractiveness.
you have to commit to smoke.
So actors are drawn to either not smoke or to smoke and tend to shy away from this level in the middle. So the model is modeling the change over time. Okay, so as they're changing, this is getting at kind of the distribution at later points in time. And so they're drawn to have this kind of distribution over time. This might mean everybody's a lot of people are increasing. It could mean some people are decreasing. We don't know the direction of change here. We just know that they're drawn toward this distribution.
So why do you have a 3-level variable? Why not just have a yes, no smoking?
That's a good question. Why did we do that? We had a reason, and I don't know the smoking literature as well. I think it was something we pulled from the smoking literature, but we could. Yeah, actually, I wish we should. I wish we did, because we did some subsequent stuff that this got complicated.
There's nothing about like sort of that being a transition
No. So
point
okay.
towards one or the other or something.
Well, I think part of it is, and this has to be ordinal. Our outcome has to be ordinal. And so what you really want to do is look at the distribution of your behavior. And it's really a good idea to look at that distribution and pick meaningful points to kind of break it up. So, one way would be to turn everything into z-scores, right? And just round the z-scores. So you've got -2, -1, 0, 1, 2, right? That'd be an easy way to break things up. But the model is really getting at transitions between levels of your variable. And so if those transitions are more meaningful, then the model does a better job of detecting effects. Okay, so going from 12 to 20 cigarettes may not be very meaningful, but going from, and then again, we pulled that from looking at the data, and it's got this U-shaped distribution. So I think we saw there's people who are smoking a lot, people who aren't, and then there's and a lot of people who are kind of in this middle zone, and that seemed important for us to capture. And so there's, you can think of transitions between, you're trying out smoking, and you're kind of hovering around in there, but not for very long, because you're going one or the other. Yeah.
So one way to read the y-axis on the graph, how sort of absorptive each state is?
You could think about that. Yeah. It's really, again, it's the behavior function, but that's what ultimately is. Yeah.
Okay.
I'm not sure anybody else can hear that. But
Oh, how absorptive each level of the behavior is. Yeah. Okay. Right.
Sorry, I still find this hard to understand, I guess. So, there's so much longitudinal data in the fractal field that it's useful looking at it in like transitions or past periods of time. Is there like a sentence that you can
For the linear and quadratic shape, it's really smoking is distributed as a U shape. That's these effects.
at time two?
Well, you're
What causes the change? What's the strong indicator that can cause the change?
So in the sense, it was like whether or not your smoking behavior and your link to people, does that have the impact on your change or causing the change?
right. So, a couple things. If you do want to get at, you could include effects here for time. If there's a tendency to increase over time, you can include time as a covariate. And you've got at least 3 waves, and you could get at there's more likely to be adoption over time. That would be one way to get at that temporal trend. And you could interact that with any kind of effect as well. If you wanted to get at, do some things, does smoking itself become more likely, or some things become more predictive of smoking over time? But here again, we're just predicting just changes. Yeah.
Sorry for that. If you're modeling time, how do you include age, or could you include a changing covariate for age?
You could, but I mean, everybody changes at the same rate.
Right. Yeah.
So it's really just getting at if you're older versus younger, you have a greater tendency.
Or how do you even causality of time versus age?
Again, it would. Right. So you're controlling for this. If you've got an increasing, right? Can you get at that? If you've got increasing, you can't really get
Only
at
if
that.
they're on radically different scales. So if you
Yeah.
have times over weeks and different cohorts of age, then it would be sensible. But if you have age in years and waves in years, then you just have linearity. So.
Right. You would need multiple cohorts,
Yeah.
grades or ages. Yeah.
But essentially, then this would be getting at within time slice age differences compared to cross time.
Right. Right.
I mean, I've always thought of this. I've always thought of these first three parameters as essentially a complicated version of the intercept.
Yes.
Right. So
That's a great way to think about it.
The rate is telling you the temporal intercept is how much overall variability in time you're getting, whereas the linear quadratic shape is effectively giving you the attractor space, and everything else then is deviations from that. Is that fair? That's
a great way to think about it. They're really, I mean, most people don't spend any time talking about that because all it is yes, the intercept. But people constantly misinterpret it. So that's why I'm spending probably
so when they
too
do
much
talk
time.
About it, they talk about it wrong.
Right, exactly. So that's why this is here. Okay.
Are there any behaviors where you would add a higher degree of polynomial to see different shapes or certain procedures?
Right, you could. I mean, you just really look at the distribution, and you're trying to kind of get the row, telling R how to find a certain row in that table. And it's saying, look for a row that's got, look for a row in, this object that's got avsim is the short name. I forget did we look at the short name in here? Here's the short name. Okay, that's the easy way to identify effects here. Okay, find avsim. There's going to be probably 6 avsims in here because there's, again, evaluation, endowment, creation. There's smoking. There's drinking. So there's a lot of versions. So we're going to say look for this row, but let's look for one where friendship is the outcome and drinking is the what we're going to measure similarity on. No, other way around. We're looking at drinking as the outcome, and we're looking at similarity among friends. Okay. Friends are our only network, so that's kind of obvious. If we had multiple networks, though, we could say, let's look at similarity among friends. We have another effect for similarity among maybe people who we, maybe an advice relation or a mentor relation or something like that. Okay. All right, so running this should get us an effect to our model, and it's telling us it set this effect. It's going to include it. It's not fixing it to a certain value, and it's not testing whether we want to include it. Let's see, how am I doing on time? All right. So maybe this is a good time to mention. So with Siena models, kind of a good strategy is to start simple with a simple model and then slowly make it more and more complex. Start with small model, simple, straightforward effects that you expect to be there, and then slowly add more complicated effects. And so one way, again, because this is so time intensive, you really can't try out every model specification like you'd like. One thing that you can do is estimate a reduced model, and then you can kind of ask the question, well, am I really fitting? Here's an effect I want to add. Should I add it? And you can do something called a score test that will give you some indication that, yeah, it looks like this effect, the statistic for this effect, we're not really fitting it very well with this model. So you might want to add it to get a better fit for this statistic. And you can estimate that without actually including the effect in the model. So in essence, what you can do is estimate this model that has 12 effects and say, well, I'd like to consider these other 5 effects. Should I include some of them or not? And you can estimate this 12 effect model. Maybe it takes a minute to run. If you added all 5 effects, maybe it takes a couple more minutes to run. Not a big deal, but when you get big networks, you're talking about hours and maybe even days. So you can kind of provisionally test whether effects should be in a model, and this is telling you whether or not you've set it to be an effect you might want to include. Okay. All right, let's include a few more. Let's test whether being an isolate affects drinking behavior. And then let's get some selection effects here. So do drinkers have more or less friends? Is there homophily on drinking? And are drinkers more or less popular? We can also add effects for some control variables. For some of these, you notice I've listed a few effects on the same line. Reciprocity, transitive triplets, transitive reciprocating triplet cycles. Some of these very simple effects that don't need more descriptors to find where they are in the effect object. You can just add them, list them, and include multiple effects. Same thing for here. We can include this fake attribute as an eagle effect, an alter effect, and a homophily effect, all on one line. All right, that's probably enough. No, we've got one more here. Let's test for whether or not this attribute affects drinking behavior. All right, so now when we look at the model, we see we've got 24 effects. All right, here are all of the effects we've listed. Good idea to check that before you run your model, because your model might take a while. If you get one of these wrong, you'll kind of get an error, or it'll tell you that you couldn't find an effect. But sometimes you miss that if you're creating dozens of effects and not looking closely. So go back and check before you get started. All right. We're going to set up some estimation options here. This project name is useful because that's where the full model results get written to. So you'll get an output, kind of the summary of the model on the screen, but there's a lot more written out that is useful. Okay, and then we're going to run this. Okay, and you get this nice picture of Siena. And Siena tells you which phase it's in. I mentioned the 3 phases earlier. It tells you which phase it's in, how far along in each phase. Current beta estimates. These autocorrelations are useful to know if your model's kind of getting off along the way. What you want is that kind of these betas are getting closer and closer to being better values, and you're narrowing in on a solution. And so over time, these correlations between the betas at, across simulation runs, these should get smaller and smaller and smaller, meaning and eventually down all the way to 0 or negative. Okay, meaning you're getting pretty close. We missed that. That last column was deviations. Okay, that's actually taking the target statistic. Every target statistic for each of your effects, and the last simulation run, how far off you were. And what you want is that, again, you're getting closer and closer over time. If you've got a poor fitting model, sometimes it'll show up during the run. You can look and see that this effect, I'm way off. This effect is huge. The deviation is really big. I'm not fitting that very well for some reason, and you can kind of use that to figure out what a better model specification might be. So, question?
The quasi-correlation, you said that it's a correlation between the current parameter values and the previous iterations, or did I misunderstand that?
No, that would be high.
Yeah,
Right.
that's why I was confused about it.
What is that?
Must be the change, because there'd be no variance if they were the same. So.
Yeah, because you want negative, meaning that kind of you're jumping around on either side of the solution. So if it's the change, you're getting a positive jump followed by a negative jump followed by.
Oh, so if the correlations go negative, it means it's no longer approaching the optimum in the parameter space.
Yeah.
Okay.
Right. This is a good time to mention that one of the things up on Tom's website is the algorithm that is used for estimation. So the equations and really how they wrote the algorithm for all of this. It's almost an 80-page document. Walks through each of these steps. So if you really want to know, as well as he writes the statistical papers too. That he's got a great one on kind of also the algorithm. Right. Okay, so results. Yes, let's look at. All right, I'm going to stop in just a minute, I promise. But let me show you two things. First of all, this maximum convergence ratio right here is the first thing you want to check in terms of convergence. This should be less than 0.25. Okay, that's a bad model. If you have an old version of our Siena, this may not pop out right here because it's only recently that I think we've realized how important kind of fitting this measure of convergence is. This measure of convergence is based upon this third column out here, which is the convergence for each effect in the model. It's the T ratios, okay? And you want T ratios that are quite small. Meaning that, again, you're simulating networks that are right on that, you're distributed right around that observed value. Here we see that anything greater than 0.1 is kind of problematic. So these triadic effects looks like they're the root of the problem here. Okay, so I'm not even going to look at the rest of the model, okay, because convergence is it's not so poor that it sometimes this might be 3, 4, 5, 10. That's kind of really cause for concern. Maybe the model really specified a bad model. This is pretty close, meaning we probably just didn't let the algorithm run long enough. So we could do a couple of things. As you get to know your data better, you can actually figure out the initial algorithm, the initial run. Sometimes that phase 2, if you make it just a little bit longer, instead of 4 subphases, 5 subphases, can really improve fit. It can also take twice as long. So you don't want to just add a bunch of subphases bunch of iterations that you don't need. Some networks, it's really easy to hone in on a solution quickly. Others, it's not. So the first thing you can do, though, is take these estimates here, use them as starting values, and do this all again. Okay, and that's with a just slightly poor convergence. That's a good approach. Really, what we're going to do is just change this previous answer here to use the previous object, and I'm bumping up. I think my first example only used one of the clusters. I'm going to use 3 of mine and see if it goes a little bit quicker. All right, so here we go. We should be getting closer. I get really tired of looking at the screen. During grad school, I had a buddy in my cohort who decided to do a dissertation using Sienna models, and he literally would stare at the screen for one of the ad hoc schools took a month to run. This was before.
Model if you're willing to wait for it for a month.
he was finding computers all over, just everybody's computer, finding processes everywhere just to set up different models. So, all right, we're done here. Here's my, all right, a little bit better, not great. We could keep going a little bit or find a better model, or maybe, having fake data in here is the problem, and I'm not really sure. Let's see, yeah. All right. So I'm going to stop there. We can get, these are estimates, standard errors. They're really, they follow a normal distribution, so you can just divide the estimate by the standard error, get a t-value for significance. Here's some script here that does that for you. Adds some nice stars, or p-values, I think. All right, I missed a step here. Oh, I see what I did. Okay. All right, there we go. We've got some p-values, so we know what to do with it. I'll just tell you the rest of this has some goodness of fit tests. Some of these you need to run a function that's found at the end to figure out how to calculate some statistics that from iGraph. You can test for whether or not. So Siena assumes that each effect operates the same during each observed transition period. So reciprocity is the same from time 1 to time 2 as the same from time 2 to 3, etc. May or may not be realistic, so we can actually test that if we want using a time test. We can test that basically effects are constrained to be equal for each period in time. And if they're not, we can free them up so that we have effects differing. All right, and then a couple of functions here. I showed you the ego-alter selection table earlier. So there's some script to create one of those. We can do the same thing with influence. I don't know how. All right, it didn't. That's what I have. When I skip ahead, that's what happens. You'll have to trust me that you can do the same thing with influence. But sometimes, just seeing those values is a lot more intuitive than seeing the predicted values, and is a lot more intuitive than just looking at coefficients. So that's what I'd recommend. All right, I'm going to stop. It's noon. We're hungry. And if people have questions later, I'm here till 1, and then on email after that. So.
Thank you so much.